Intercepts and zeros. Recall that the intercepts are the points at which the graph crosses the axes, and a zero, which we're just now defining, is an input, so the zero is the input, that makes the output equal to 0. So, given this function, f of x equals 1/2 x plus 4, we're going to test each of these values of x, each of these two inputs, to see if either of them is a 0. And the way we're going to do that is by plugging them in for x. So here we're going to evaluate f of 0, which is 1/2 times 0 plus 4. Of course, the 1/2 times 0 term vanishes, so we get f of 0 equals 4. So we would say, let's see, for 0 to be a 0 of this function, it has to be an input that gives me an output of 0. Since this output is not equal to 0, we would say, no, this is not a 0 of the function. So the number 0 is certainly possible to be not a 0 of the function. Going on now to x equals -8, we're going to check this by taking f of -8, which gives us 1/2 times -8, which I'll write as -8 over 1 plus 4. And then, of course, we have a common factor of 2 here. So this gives us -4 plus 4 overall. And because this is equal to 0, f of -8 is equal to 0, we would say yes, this is in fact a 0 of the function. Furthermore, we're then asked to find an ordered pair on the graph of f that's based on this 0. So if we go back to the statement that f of -8 is equal to 0, and keep in mind that this is following the standard format f of x equals y, then we can do a little mapping here and say, okay, it looks like -8 would be a value of x and 0 would be a value of y, so my ordered pair would be -8, 0. And this gets us to an important result, which is that the x-intercepts of a graph are the real zeros of the function. The way we get from this point, this ordered pair, to this result is by observing in our ordered pair that because the y-coordinate is equal to 0, we know that this point must lie on the x-axis, and therefore it is an x-intercept of the graph. So we're going to use this important result that x-intercepts of a graph are the same thing as the zeros of a function to come down here to this graph and find the zeros. I'm going to answer the last question first because it's what we just finished talking about. So I'm going to find the zeros of this graph by just locating those x-intercepts. And I would never write a 0 as an ordered pair because remember, the definition is that a 0 is an input to the function that makes the output 0. So these are just inputs. These should just be numbers. It looks like we've got one at -3, another one at -1, and another one at +2. I'm just going to list these as numbers. I would never list zeros as ordered pairs. Even though intercepts can be listed as ordered pairs, and in some sense they're the same thing. That's because the intercepts really do refer to the points on the graph. So each of these zeros corresponds to an x-intercept, which I will write as an ordered pair. So we've got -3, 0, and -1, 0, and 2, 0. But the intercepts also include the y-intercept, so let's throw that one in magenta. It looks like we have a y-intercept down here at -3, and that's going to be the point 0, -3. So sometimes it's helpful to list the intercepts as ordered pairs so that it's really clear whether they're x or y intercepts. For the domain, again, I want to just think about what all the x values are on this graph. When the graph appears to kind of run off the end of the grid, it's an implied arrow, so I'm going to draw in the arrow that's not already drawn for us on this graph. And I can see that my largest x value is right here at 2, and then the graph goes in this direction. And where I have an arrow on my graph, that's going to translate to an arrow on my set of x values as well. So my domain would be the set from -infinity up to +2 with a square bracket. My range looks like it has the largest y value here at +2, and then the rest of the graph lies below that, so I start filling in downwards. And again, when I come to that arrow on the graph, that's going to translate also to an arrow on my set of y values, so I'm going to express the range. Turns out to be the exact same set as the domain from -infinity to 2, but for different reasons.